Hello, this is Brian Kinghorn, and this is the third in our series of videos on genetic markers, and today we're going to talk about managing sex-linked markers. So that's where you have genetic markers on the sex chromosomes, and in many cases that complicates things a little bit, but it also can bring opportunities such as the ability to use feathering traits such as color or style of feathers in day-old chicks in order to tell which ones are the boys and which ones are the girls. So here is a sex-linked example, and we've got a male XY and a female XX being mated, and there is a locus on the X chromosome where the first allele, number 1, is dominant over the second, and allele 1 gives a red colour. So the male carries allele 1 on its X chromosome, and therefore it is dominant red, and this female doesn't have a marker number 1, only 2,2, and therefore it's white. And when we make these two together, any female offspring must have inherited the X chromosome from the male, and therefore they inherit the number 1 allele and are red. Whereas all males inherit a Y chromosome from the male, they get the female's X2 allele, and therefore they are all white. And this is a useful sort of cross because in this situation all the females are red and all the males are white. And of course in birds it's the other way around. The heterogametic sex is not the male, which is XY in mammals, but it's the female, ZW in birds. What we can do when we're handling this in Matesel is to treat the Y chromosome as a null allele, possibly allele 0, on the X chromosome. So we could represent the Y chromosome as X0, like an X chromosome with a 0 allele on it, and that would give exactly the same diagram, replacing Y with X0, but we'll stick with using Y as the descriptor. Y is essentially just an X chromosome. It's just not a particularly good one, and it's got quite a lot missing, as is the case in our example. Now we have 3 alleles, not just 2, and these are 1, 2, and Y. And so the header in our data file may look something like this. Here it is described in the manual. So we've got 3 alleles and 6 genotypes in the data file representing the possible genotypes that we can have. In this case, we're treating the heterozygotes as combined, whereas if we had a 3_9, we would be separating genotype 1, 2 from 2, 1 in this fashion. But we'll stick with this one in the example. So let's look at this in the context of a data file, and this is the example we're going to use. Here we have G for genotype with 3 alleles and 6 genotypes represented, which I'll describe in a moment. I've labelled the locus SL for sex-linked, and the labels for the alleles are 1, 2, and Y. Looking in the manual again, it's the same here, with genotypes 1 to 6 are the numbers that are going to be put in the columns, so here they are here. Let's first of all look at a 2 allele example. Here it is, 1, 2, and 3 as we have here. So the 3 genotype labels that we put in the data file are 1, 2, and 3, and you can see them down this column. And they represent the genotypes for alleles 1 and 2, 1, 1, 1, 2, or 2, 1 in fact, because we're only looking at 3 rather than 4 genotypes, and 2, 2. So these are the 3 genotypes that are in the data file. Over here we have up to 6, and here they are the numbers. These are the numbers that are entered in the file, and the representation of the genotypes is 1, 1, 1, 2, and 1, Y, which is the 3rd allele, 2, 2, 2, Y, and Y, Y. And of course, Y, Y does not exist, and we'll never find that coming up in the data set. So just before we move on to the example, let's look at this first individual as the genotype number 3, which is equal to genotype 1Y, or indeed Y1. If we look back here, you'll see I have a field called SL genotype, and I've not used Y, but I've used 0 to represent the null allele, and that's because it makes this column numeric, and this will be treated as a trait, and that could provide extra information when we look at the analysis. So let's have a look. Here's the run that has been made, and the thing you'll notice straight away is that our sex-linked locus, which is the second marker locus here, has got many more histograms in it. That's because there are 3 alleles, and therefore there are 9 different genotypes. Even although we're only representing 6 different genotypes in the data set, Matesel has the ability to separate the different heterozygotes, so that if you look at the genotype probability for 1, 2, here it is in this histogram, that's quite different from the genotype probability for 2, 1. And Matesel has the ability to separate these because it knows the direction from which the different alleles came, from father and from mother. A couple of other things to notice here. Of course, YY never exists in the data file or in the progeny, and that's why we have a 0 probability of YY. But we also have 0 probability of 2Y. That is, we've got 0 probability of getting a Y chromosome from our mother, because this is ordered father-mother. So we've got 0 for 2Y, and we've also got 0 for 1Y. If you want to check in your data file that you've got the inheritance pattern correct, you can click this icon up here, and that will bring up this window with Pedigree Viewer. We can ask to look at the SL genotype field, where you can check pattern of inheritance is logical for your situation. I'll just make one manipulation here. Let's go to the frequency of the number 1 allele up here. So I click on this and say I want to increase the mean of that. I'm going to make that a very strong increase in mean, just to see how far it can go. And if we resume, we'll see that we get no values greater than 0.75 for the frequency of allele 1 in individuals. And there is a reason for that. Let's look at that. Here we are. If we look at the matings we make between the sires and the dams, with all the different genotypes that are available, well, with a 1Y sire by a 1-1 dam genotype, the progeny will have no number 2 alleles, and this is the 2 different types of male and female progeny that you'll have. The reported frequency for the number 1 allele will be 3 out of the 4 different sites, and that's why we get a maximum of 3/4. Now that may be what you want to use, because it is in fact a 3/4 frequency of that allele, considering that the Y chromosome is a null allele. However, if you want to convert all these probabilities into corrected frequencies, simply divide by 0.75. In other words, we're looking at summing these things over 3 sites rather than 4. And that's how you get corrected frequencies if you want them in that format. Well, that's the end of this video on sex-linked markers. The next video is going to be on handling multiple recessive lethals over potentially hundreds of different loci. See you next time. Thank you for listening.